Hi everybody, this video is all about simple regression. Simple regression is so easy that I had my 6th grade robotics class doing it. So they took their robot and they were graphing power by distance. So they put their robot at 10% power and see how far it went. They'd put it at 20% power and see how far it went. 30% power, see how far it went. And we got this nice set of raw data. We drew a line of best fit, and then we can actually make some predictions. So at 25% power, I can go over to my line and say, okay, I'm predicting a distance of about 2,000 centimeters. I will say they were a little bit shocked and thought their robots were broken when they put in 0% power and got 0 distance. And that's all we're doing. We're trying to examine relationships by taking it further and starting to predict one from the other. So prediction is the key here. There are lots of types of regression. There is simple regression, which is what we're focusing on in this class. Multiple regression takes us further and adds in predictors. We'll learn that in intermediate stat, and I'll introduce you to canonical correlation in intermediate stat as well. And HLM is its own course if you're really interested in multi-level modeling. So let's start with level of measurement. Both variables have to be continuous. Just like in correlation, we have to have both continuous variables. We cannot use categories for these. Sort of. We can make dichotomous independent variables work. So we could do a dichotomous predictor of male, female, white minority, Colorado, California, but it's not ideal. And that leads us to talking about what the heck is dependent and what is independent. So an independent variable is one that's not really changed or affected by other variables you're trying to measure. So typically these are the ones that you're trying to see, does it cause a change in another variable? In our case, these are going to be our X variables. These are going to be our predictor variables to see, does this predict something else? The dependent variable, on the other hand, is something that does depend on other things. This usually is the gold of our study. The dependent variable is the focus. It's the outcome variable. It's the one that we're really interested in seeing. Can we find things that affect it? So in our case, this is going to be the Y variable, our outcome variable, our predicted variable. So I want you to take a minute. We're going to pause the video, and I want you to look at the comparisons, the pairs, and see which one would you say is independent and which one is dependent. So pause the video and brainstorm. So if you thought this was a trick question, it kind of is. Some of them are more obvious than others, and it comes down to you're the researcher and you have to decide this. So if we're looking at math, achievement, and gender, you're not going to change my gender based on my achievement. So in this case, it's pretty obvious that gender would be X, my predictor, and math achievement would be my outcome variable. It would be my Y. But hours of sleep and caffeine are a little bit harder. So if I didn't get enough sleep, I might take in more caffeine. Or if I had too much caffeine, now I may not sleep as well. So we would have to really define the relationship between those two. So let's look at the example of hours worked and salary. So the thought behind it would be the more hours that you work, the more salary you would gain. Maybe, maybe not. So a research question would be, do the number of working hours predict an employee's salary? And we would use regression for this. So we're going to take the independent variable and predict the dependent variable. So which one would be X and which one would be Y? In this case, our Y would be our employee salary. That's our dependent variable. That is our predicted outcome. And then our X is going to be working hours. So that's going to be the predictor variable to see, does working hours predict salary? And now we get to start writing these really cool equations based on this. So this example is going to be salary, our Y, equals beta 0 plus beta 1 times hours, our X. Here's the same equation. Do not overthink this. You have seen this since high school. Think back to those hopefully not nightmares of Y equals mx plus b. Those were the same things. When you were talking about slope and rise over run, This is the exact same thing. We're just in statistics now, and so we're going to be jerks and use our own statistical language, hence beta 0 and beta 1. But it's the same thing. So for beta 0, that's going to be our y-intercept. That is just the spot where the line crosses y. That might be 0, it might not be 0. Our beta 1 is the slope. So this is the rise over run thing that you remember. And our slope in this case is actually going to be our correlation coefficient because we're just looking at simple regression. That is not the case when we get to multiple regression. And then x is the single independent variable. So again, you can use x and y in these equations, but I'm a huge fan of writing in the actual name of the variable, mostly for my own sanity. So we start with a scatter plot because we want to see the relationship between the two variables. We can see that this one has a pretty clear positive relationship, so as one is increasing, the other is also increasing. But we're taking it further, and we're going to add a line of best fit. So we're going to put in our data, and we're going to add a line, and not just some random line that I can draw, because I can literally draw a line through anywhere through this and call it a best fit line. But this is a mathematical equation based on the least squares to find the best fitting line. And here's what we're trying to do. We have some of these guys that are right on the line. So we can see this guy, this guy, this guy, this guy, and this guy are all on the line. But the other ones aren't. And so the residual, also called the error, for this guy is positive because he's above the line. This guy's error term is negative, he's below the line. Above the line, below the line, above the line, above the line, below the line. And the idea is that we minimize, that they cancel each other out. So all these guys above the line cancel out the guys below the line, which gives us 0 error. If it is a true line of best fit, then our residuals are 0 when you add them up. So let me be clear that this line goes through more data points specifically, but it is not the line of best fit in this case, because the error for this one guy is not going to cancel out all these guys way down here. So the line of best fit would actually be kind of more in between, and nobody is probably going to be directly on the line in this case. And that's okay. It is also very, very rare to have a perfect line where every single data point goes through it. I'll show you a quick calculation in case you want to see it, but we are going to do this with Excel, and you are welcome. So we have y equals bx plus c. B equals the correlation coefficient over the standard deviation of y, standard deviation of x. C equals y, the mean of y minus b times the mean of x. So if we wanted to predict life satisfaction from a sample of 121 30-year-olds, we've got the mean and standard deviation for life satisfaction, the mean and standard deviation for salary, and then we have the correlation coefficient between them both. And we're just going to plug in numbers. So beta 1 is going to be 0.0002. Beta 0 is going to be 5.49. And then we write our equation. This is the cool part, is that we write our equation, and this is the focus of all of it. We can also find our residuals there. But if I have a salary that is known, I can now predict my life satisfaction by going back up here. So if I have a salary of $30,000, I'm going to take 0.002074 times $30,000 plus 5.94, and that's going to be my predicted life satisfaction score. I will say regression does have assumptions of normality, so we want both variables to be normally distributed, and we want them to have a linear relationship. There is also assumption of independence of error and homoscedasticity, but we'll come back to those more in depth in intermediate statistics. So here's your need to knows. Independent variable, this is our predictor variable, this is x. Dependent variable, this is our predicted outcome, this is y. Also make sure you know what beta 0 and beta 1 mean. And of course, remember that our level of measurement has to be interval or ratio, so we need them to be continuous variables. Next, we'll look at how to do this in Excel.